Welcome to Dreamosaurs, where we drift through ancient oceans and explore the deep mysteries of prehistoric seas. Tonight, we're going to sink beneath the surface of the Mesozoic waters, where creatures as magnificent and alien as any dinosaur glided through currents that no longer exist, hunting in oceans whose shores have long since vanished into geological time. Close your eyes for a moment and imagine standing on a shore that existed when the world was young and utterly different. The sand beneath your feet is warm, heated by a sun that shone with slightly less intensity than it does today. Yet the air around you feels thick with humidity, pregnant with moisture from an ocean that stretches endlessly before you. This is not the ocean you know. This sea is warmer, its waters bathed in tropical heat, even near what would someday become the polar regions. There are no ice caps in this world, no frozen poles to chill the currents. Instead, the deep waters themselves run warm, circulating through ocean basins in patterns entirely unlike those of our modern seas. Breathe in deeply and let yourself relax. In this moment, you're safe on the shore, watching the waves roll in with a rhythm that hasn't changed in hundreds of millions of years. But beneath those waves, in waters that might reach temperatures of 35 degrees or more, even in regions we would call Arctic today, an entirely different world thrives. A world of hunters and hunted, of creatures that return to the sea from the land and, over millions upon millions of years, transform themselves into beings perfectly suited for an aquatic existence. The story of the Mesozoic marine reptiles begins not in the ocean, but on land. Picture the world as it existed 250 million years ago, at the dawn of what we call the Triassic period. The planet was just beginning to recover from the most catastrophic extinction event it had ever known. The Permian-Triassic mass extinction had erased as much as 95% of all marine life, leaving the oceans eerily empty, like vast liquid deserts waiting to be repopulated. The land masses were still locked together in a single, immense supercontinent called Pangaea, and life was struggling to regain its foothold in a world that had been devastated beyond imagination. But nature abhors a vacuum, and into these empty oceans, various groups of reptiles began to venture. Some were small, lizard-like creatures that perhaps waded in the shallows at first, snapping up fish and small invertebrates. Others were descendants of different reptilian lineages, each finding their own pathway back to the water. These pioneers faced a world of opportunity. The oceans were warming, recovering from the extinction event. Shallow seas were beginning to flood across the continental margins as the planet's climate shifted into a greenhouse state. And with relatively few competitors, these early marine reptiles found themselves in an environment where they could experiment, adapt, and evolve. As you settle into a comfortable position, letting your breathing slow and deepen, imagine yourself drifting back through time. The continents are moving beneath you, sliding across the surface of the planet like pieces of a vast puzzle being rearranged. Pangaea is beginning to fracture, to pull apart at the seams. As it does, new ocean basins open up. The Tethys Sea, a vast tropical ocean, grows wider and wider, creating new coastlines, new shallow seas, new opportunities for life to flourish. In these early Triassic seas, the first marine reptiles were still quite primitive in their adaptations. The Dinosaurs, whose name means roughly southern lizard, were among the most successful of these early pioneers. Imagine a creature that was part seal, part reptile, with a long, flexible neck and a body that retained much of its terrestrial heritage. These animals could grow impressively large, with some species reaching lengths of 6 meters or more. Their skulls were flattened, equipped with a meshwork of slender, conical teeth that interlocked when the jaws closed, creating a perfect trap for slippery fish and squid. The nothosaurs had limbs that were beginning the transformation from legs into flippers, though they retained functional elbows and knees. They likely spent time both in the water and hauled out on shore, much like modern seals. Their long necks gave them an advantage in hunting, allowing them to extend their heads into schools of fish, while their bodies remained relatively motionless. Recent discoveries have even found fossilized tracks made by these animals, preserved in ancient seabeds, showing us exactly how they moved. The tracks reveal that nothosaurs used their forelimbs for propulsion, rowing themselves along the ocean floor, their paddle-shaped feet digging into the sediment and pushing them forward. Alongside the nothosaurs lived an even more peculiar group of marine reptiles called the placodonts. If the nothosaurs were the seals of the Triassic oceans, the placodonts were something else entirely, creatures that seem almost impossible when you first learn of their existence. These animals were built for a very specific lifestyle, one focused on crushing hard-shelled prey. Picture a reptile with a body that, in some species, became heavily armored with bony plates, much like a turtle, though they were not related to turtles at all. Their heads were broad and flattened, and inside their mouths was a remarkable adaptation. They had developed crushing teeth, not just along their jaws, but also on the roof of their mouths, on the palatine bones. These teeth were broad, flat, and immensely powerful, capable of crushing through the shells of mollusks, brachiopods, and other hard-bodied invertebrates that carpeted the seafloor. The placodonts would swim down to the ocean bottom, their heads angled downward at about 20 degrees, an ideal position for feeding along the substrate. There, they would gather up shellfish, crushing them methodically with their specialized dentition. Some placodonts developed such heavy armor that they must have spent most of their time on the seafloor, lumbering along like armored tanks in slow motion through the clear Triassic waters. Recent studies have shown that placodonts replace their crushing teeth in a unique pattern, one side of the mouth at a time, ensuring they could always continue feeding without interruption. But perhaps the most unusual of all the Triassic marine reptiles were the thalattosaurs, whose name means sea lizards. These were serpentine creatures with long bodies and tails that they used to undulate through the water. Some had very peculiar skulls, with snouts that curved downward in an almost beak-like fashion. They filled ecological niches that would remain empty after their extinction at the end of the Triassic, and were still piecing together exactly how they lived and what they ate. The mystery of these creatures adds to the alien quality of the Triassic oceans, reminding us that evolution explored pathways in the past that have no modern equivalents. Let your mind drift now to the open ocean, away from the coastal shallows where the nothosaurs and placodonts hunted. Out here, in the deeper waters, swam the ichthyosaurs, and these were creatures unlike anything else. The ichthyosaurs, whose name means fish lizards, achieved a level of aquatic adaptation that seems almost miraculous. They looked remarkably like dolphins, with streamlined, torpedo-shaped bodies, powerful tail flukes, and dorsal fins on their backs. This similarity is not because they were related to dolphins in any way, but because of convergent evolution, where completely different animals evolve similar body plans to solve similar problems. The earliest ichthyosaurs appeared around 248 million years ago in the early Triassic, making them among the very first reptiles to return to the sea. These early forms were still somewhat eel-like, without the sophisticated tail flukes of their descendants. But evolution worked quickly on these pioneers. By the Middle Triassic, ichthyosaurs had already developed the classic dolphin-like form that would characterize the group for the next 160 million years. Imagine swimming alongside one of these magnificent creatures. Its skin would have felt smooth under your hand, not scaly like a lizard's at all, but covered in skin similar to that of a shark or dolphin. The creature's eyes would catch your attention immediately, for ichthyosaurs possess the largest eyes relative to body size of perhaps any vertebrate that has ever lived. Some species had eyes as large as dinner plates, immense organs designed to gather every available photon of light in the dim depths of the ocean. These enormous eyes were protected by a ring of bony plates, a scleral ring that helped support the eye against the pressure of deep dives. For decades, scientists debated whether ichthyosaurs were truly ocean-going reptiles or whether they had to return to land to give birth, like modern sea turtles. The question was answered dramatically when fossils were discovered showing pregnant females with embryos still inside them, and in some heartbreaking cases, females that had died in the act of giving birth. These fossils, preserved in the fine-grained limestone of places like Holzmaden in Germany, show baby ichthyosaurs emerging from their mothers, frozen in stone at the moment of birth. The discoveries revealed something fascinating about how these animals reproduced. The earliest ichthyosaurs gave birth to their young head first, just like land mammals do. This suggested that live birth had evolved on land in their ancestors before they returned to the sea. Later ichthyosaurs, however, switched to giving birth tail first, the way modern whales and dolphins do, which prevented the newborns from drowning if the birth process took too long. The ichthyosaurs varied enormously in size across their long history. Some were barely larger than a human arm, while others grew to truly gigantic proportions. The largest ichthyosaur ever discovered, a species called Shawnosaurus sicaniensis, stretched 21 meters in length, rivaling the size of modern sperm whales. These giants lived during the late Triassic and likely fed on squid and other soft-bodied prey that they could gulp down whole. Their fossils have been found in what were once deep ocean basins, suggesting they were pelagic animals, creatures of the open ocean rather than coastal waters. Most ichthyosaurs, however, were smaller and more agile. They hunted fish and squid with quick, darting movements, their streamlined bodies allowing them to reach impressive speeds. Recent studies suggest that many ichthyosaurs were capable of controlling their body temperature, maintaining it at levels similar to modern whales, between 35 and 39 degrees Celsius. This warm-bloodedness, or endothermy, would have required them to eat enormous quantities of food to fuel their high metabolism, but it also would have allowed them to hunt in cooler waters and to maintain burst swimming speeds that cold-blooded marine reptiles could never match. The skeleton of an ichthyosaur reveals the extraordinary adaptations that allowed these animals to thrive in the ocean for so long. Their vertebrae were tightly packed along most of the body, creating a rigid, powerful platform that could transfer swimming force efficiently. Only near the tail did the vertebrae loosen up, allowing the flexibility needed for the powerful side-to-side sweeping motion that propelled them through the water. This is remarkably similar to the vertebral structure of modern tuna, another group of fast-swimming predators that use their tails for propulsion. The limbs of ichthyosaurs had transformed so completely from their terrestrial origins that they bore almost no resemblance to legs at all. The bones were short, flattened, and polygonal, fitting together like tiles in a mosaic. The number of digits actually increased beyond the 5 that tetrapods usually possess, and each digit contained many more bones than a land animal's fingers or toes would have. This created paddles that were rigid enough to push against the water effectively, but flexible enough to make fine adjustments for steering. Unlike the flippers of plesiosaurs, which provided the main propulsion, ichthyosaur flippers were used primarily for control and stabilization, much like the pectoral fins of a shark. Consider the daily life of a typical ichthyosaur, perhaps Stenopteroides, one of the most common species from the early Jurassic. This animal, about 3 meters long, would spend its entire life in the water, never coming to shore, never resting on land. It would sleep at the surface, half conscious, one eye open, much as modern dolphins do. When hunting, it would use its enormous eyes to scan the water, searching for the telltale flashes of light reflecting off fish scales, or the darker shadows of squid moving through the depths. When prey was spotted, the ichthyosaur would accelerate with powerful strokes of its tail, its body becoming a living torpedo. The jaws would open, revealing rows of sharp, conical teeth, each one slightly curved backward to prevent struggling prey from escaping. The strike would be fast, precise, and usually successful. Small prey would be swallowed whole, sliding down the long throat into a stomach that could expand to accommodate large meals. Larger prey might require multiple bites, the ichthyosaur shaking its head violently to tear off manageable chunks. Fossil evidence tells us remarkable things about what ichthyosaurs ate. In the stomach regions of exceptionally preserved specimens, paleontologists have found the indigestible remains of their last meals. Fish bones are common, as are the hooks from squid tentacles and the hard beaks of cephalopods. Some specimens contain hundreds of these hooks, suggesting that the ichthyosaur had consumed many squid in a feeding frenzy. In one extraordinary fossil, the stomach contents included the bones of a baby ichthyosaur from a different species, evidence that these marine reptiles occasionally engaged in cannibalism, or perhaps scavenged the bodies of dead young they encountered. The breeding behavior of ichthyosaurs fascinates scientists because it represents an evolutionary transition we rarely get to observe so clearly. The shift from laying eggs on land to giving birth to live young in the water is a major adaptation, one that requires numerous anatomical and physiological changes. The female ichthyosaur had to evolve ways to nourish the developing embryos inside her body, to carry them without being weighed down too much to swim effectively, and to give birth in an environment where a newborn that couldn't swim immediately would drown. The fossils from Holzmaden show us that ichthyosaurs typically gave birth to multiple young at once, though not as many as some sharks and rays produce. A pregnant female might carry anywhere from 2 to 11 babies, depending on the species and her size. These babies were quite large at birth, sometimes a third the length of their mother, and they emerged ready to swim. The birthing process appears to have been relatively quick, though dangerous. Some females died in the attempt, their bodies sinking to the sea floor with their partly born offspring still attached, creating the poignant fossils we find today. Once born, baby ichthyosaurs faced a perilous world. They were prey for larger marine reptiles, for sharks, for predatory fish. Their mothers might have stayed with them for a time, offering protection, but we have no direct evidence of this. What we do know is that many young ichthyosaurs did not survive to adulthood. The fossil record shows a higher proportion of juvenile specimens than we would expect if all of them lived to maturity, suggesting that mortality among the young was high. Those that did survive would grow quickly, reaching sexual maturity within a few years. An ichthyosaur's life was likely short by modern mammalian standards, perhaps 15 to 25 years at most, though some larger species might have lived longer. They would spend those years in constant motion, hunting, avoiding predators, mating, giving birth, and hunting again. It was an existence shaped entirely by the ocean, by the demands of an aquatic lifestyle, and by the endless need to find enough food to fuel their warm-blooded metabolism. The diversity of ichthyosaurs over their long evolutionary history is staggering. In the Triassic, they range from small, eel-like forms barely a meter long to the colossal Shonosaurus, which rivaled modern whales in size. Some Triassic ichthyosaurs had crushing teeth, suggesting they fed on hard-shelled invertebrates. Others had long, narrow snouts filled with needle-like teeth, perfect for catching small, quick fish. This diversity suggests that ichthyosaurs had specialized to fill many different ecological niches, much as modern whales have done. By the Jurassic, ichthyosaurs had somewhat standardized around the classic dolphin-like form, but variations remained. Some had very deep bodies, like modern tuna, possibly adapted for burst speed. Others were more elongate, perhaps suited for efficient cruising over long distances. The Cretaceous saw a reduction in ichthyosaur diversity, with fewer species filling fewer niches, though those that remained were still successful in their respective environments. The ultimate extinction of the ichthyosaurs occurred in the middle of the Cretaceous, around 93 million years ago, during a time of significant environmental change. Sea levels were fluctuating, ocean chemistry was changing, and volcanic activity was increasing. The exact cause of their demise remains uncertain, but it appears to have been relatively sudden. Ichthyosaurs that had existed for over 150 million years, that had survived multiple mass extinctions and countless environmental changes, finally disappeared. The ecological roles they had filled would not remain empty for long. Within a few million years, mosasaurs would begin their rapid evolution, filling some of the niches that ichthyosaurs had vacated. As you breathe slowly and deeply, feeling more and more relaxed, let yourself sink deeper into the Triassic seas. The water around you is clear and warm, bathed in sunlight that filters down from above in shimmering columns of blue-green light. Schools of fish dart past, pursued by sleek ichthyosaurs, whose eyes track every movement. On the seafloor below, placodonts crunch their way through beds of shellfish, the sound of breaking shells echoing strangely through the water. And in the middle distances, nothosaurs hang nearly motionless, their long necks extended, waiting for the perfect moment to strike at unsuspecting prey. But the Triassic period would not last forever. Around 201 million years ago, another mass extinction event struck the Earth, one that would fundamentally reshape the oceans and the creatures living in them. The Triassic-Jurassic extinction eliminated many of the marine reptile groups that had flourished in the Triassic seas. The placodonts vanished entirely, never to return. The nothosaurs disappeared as well, along with many other groups. Even the ichthyosaurs, which survived the extinction, were reduced to just a few lineages, passing through what scientists call an evolutionary bottleneck. Into the empty niches left by the extinction, new groups of marine reptiles emerged and diversified. The Jurassic period, which followed the Triassic, would see the rise of what are perhaps the most iconic of all marine reptiles, the plesiosaurs. These creatures, whose fossils would later inspire legends of sea monsters and lake monsters, were unlike anything that had come before, or has existed since. Picture yourself now in the Jurassic oceans, perhaps 160 million years ago. The world has changed dramatically since the Triassic. Pangaea has continued to fragment, and the Atlantic Ocean is beginning to open up. A narrow seaway at first, but growing wider with each passing million years. Sea levels have risen dramatically, flooding across the continents and creating vast, shallow seas. The climate is warm and humid, with dense forests growing even in polar regions, though those regions experience the strange phenomenon of months-long daylight in summer and months-long darkness in winter. Beneath the waves, the plesiosaurs have established themselves as the dominant predators. They evolved from a group called the pistosaurs, creatures that emerged from the same Sauropterygian lineage that had produced the nothosaurs. But while the nothosaurs had retained much of their terrestrial anatomy, the plesiosaurs had committed fully to the ocean. Their limbs had transformed entirely into large, powerful flippers, with extra finger bones, evolved to make the flippers longer and more paddle-like. The bones of their shoulder girdles and hips had expanded enormously, providing vast surfaces for the attachment of the massive muscles needed to power these flippers through the water. And here is where plesiosaurs did something truly remarkable. They evolved a method of swimming that no other vertebrate before or since has fully replicated. They swam by flying underwater, flapping their four flippers in vertical strokes, much like the wings of a bird in flight. This gave them power, maneuverability, and efficiency in the water. Modern sea turtles use a similar swimming method with their forelimbs, and penguins fly through the water in a comparable way. But no animal today uses four flippers in the coordinated fashion that plesiosaurs did. The plesiosaur body plan proved so successful that it persisted, with variations, for over 140 million years. But within that basic plan, plesiosaurs evolved two very different morphologies, each suited to a different lifestyle. Some plesiosaurs developed short, powerful necks, and massive heads equipped with enormous teeth. These were the pliosaurs, and they were apex predators, the rulers of the Jurassic and Cretaceous seas. Others went in the opposite direction, developing extremely long necks and small heads. These were the plesiosauromorphs, or true plesiosaurs, and they represented one of evolution's most extreme experiments in body shape. Let your breathing slow even further as we explore these two groups. First, imagine encountering a pliosaur in the open ocean. You see it first as a shadow, a massive shape moving through the blue darkness below you. As it rises, its true size becomes apparent, and you realize you're looking at something far larger than any predator alive today. This is Pliosaurus, one of the giants of the Jurassic seas, and it stretches 11 meters or more from nose to tail. But it's the head that captures your attention. A massive skull, nearly 3 meters long, armed with teeth like railroad spikes. The jaws are powerful enough to bite clean through bone, and recent fossil discoveries have shown bite marks on other marine reptiles that could only have been made by these enormous predators. The pliosaurs were built for power and speed. Their short necks reduced drag and allowed their massive heads to be whipped through the water with terrifying velocity. They hunted everything from large fish to other marine reptiles, and they likely patrolled the open oceans and deep waters, ambushing prey from below. Some pliosaurs, like Kronosaurus, had skulls that measured close to 3 meters in length, with massive, rounded teeth toward the back of the jaws that could crush through shells and bones. These were animals that had few, if any, natural predators. They sat at the very top of the marine food web. Now shift your attention to the other extreme of plesiosaur evolution. Swimming through the Cretaceous seas, perhaps 90 million years ago, is Elasmosaurus, and this creature defies belief. From the tip of its small head to the end of its short, pointed tail, it measures 13 meters long, but half of that length, an astonishing 7 meters, consists entirely of its neck. This neck contains 76 individual vertebrae, making it the longest neck of any known animal. Other related species, like Albertonectes from what is now Canada, had 72 neck vertebrae, each one a small bone linked to the next in a flexible chain. For over 150 years, scientists have puzzled over why these animals evolved such absurdly long necks. When fossils were first discovered, paleontologists imagined plesiosaurs swimming with their necks held high above the water like swans, darting their heads down to snatch fish from the surface. But this reconstruction is impossible. The neck vertebrae simply don't bend enough to allow such a posture, and even if they did, the weight of the neck would pitch the animal forward in the water. Instead, these long-necked plesiosaurs likely swam with their necks extended straight ahead or in gentle curves, using them to position their small heads precisely when hunting. The mechanics of how plesiosaurs actually use their necks has been the subject of intensive research in recent years. Scientists have used computer models to simulate how these necks would behave in water, and the results are fascinating. A straight neck produces much less drag than a bent one, and the more extreme the bend, the more water resistance it creates. This suggests that plesiosaurs kept their necks relatively straight while cruising, only bending them when moving slowly or when making the final strike at prey. Recent research suggests that the extremely long-necked species were adapted for life in the open ocean, making long migrations like modern humpback whales. Their long, pointed flippers had a high aspect ratio, like the wings of an albatross, perfect for efficient long-distance cruising. Meanwhile, shorter-necked plesiosaurs with stubbier flippers lived closer to shore, where maneuverability mattered more than endurance. The long neck might have served as a stealth weapon, allowing the small head to approach schools of fish or squid without the bulk of the body spooking them. Or it might have been used for feeding on the seafloor, the plesiosaur floating at the surface while its neck stretched down into the depths below. But the neck is only part of what made plesiosaurs remarkable. Their four-flipper swimming method represents one of the most unusual locomotor systems in vertebrate history. No living animal swims quite the way plesiosaurs did, and understanding exactly how they coordinated their four limbs has required extensive biomechanical studies. Computer simulations have shown that plesiosaurs likely used their front flippers for most of the power stroke, with the rear flippers providing additional thrust and serving as rudders for steering. The motion would have been a flying one, with the flippers sweeping up and down in a figure-8 pattern, much like the wings of a bird or the flippers of a sea turtle. But coordinating four limbs is more complex than coordinating two, and plesiosaurs appear to have used different gaits depending on how fast they wanted to swim. At slow speeds, they might have rowed with all four flippers moving in unison. At higher speeds, they might have flapped the front and rear pairs out of phase, creating a more efficient thrust pattern. This swimming method gave plesiosaurs remarkable maneuverability. They could turn quickly, roll, dive steeply, and even potentially swim backward, at least for short distances. This would have been enormously useful when hunting in complex environments like kelp forests or rocky reefs, where prey could dart into cover and predators needed to be able to follow every twist and turn. The muscular and skeletal adaptations required for this swimming method were extensive. The shoulder girdle and pelvis of plesiosaurs were massive compared to those of other reptiles, forming broad plates of bone that provided attachment sites for the enormous muscles needed to power the flippers. The bones were also heavily reinforced to withstand the forces generated during swimming. In some specimens, you can see evidence of stress fractures that healed during the animal's lifetime, testament to the enormous forces these swimming muscles generated. One thing we know for certain is that plesiosaurs were not slow, clumsy animals. Fossil evidence shows that at least some species suffered from the bends, decompression sickness caused by ascending too quickly from deep dives. This tells us they were capable of diving to considerable depths, deep enough that rapid ascent would cause nitrogen bubbles to form in their blood and bones. The presence of these lesions in the bone suggests that plesiosaurs were diving to depths of at least several hundred meters, possibly pursuing squid and fish into deeper waters where light barely penetrated. We also know from recent discoveries that plesiosaurs gave birth to live young, and unlike most other marine reptiles, they seem to have given birth to single, large offspring rather than many small ones. This suggests extended parental care, perhaps similar to modern whales, with mothers protecting and teaching their young over a period of years. The fossil evidence for this comes from a specimen discovered in Kansas that shows a large adult plesiosaur with a single fetus, remarkably large in proportion to its mother. The size of this fetus suggests it was born quite developed and capable, perhaps able to swim and hunt almost immediately after birth, though it might have stayed close to its mother for protection and learning. The diversity of plesiosaurs over their 140 million year reign was extraordinary. There were species adapted for every marine environment, from shallow coastal lagoons to the open ocean. Some had teeth adapted for catching fish, with sharp points and slight backward curves. Others had teeth better suited for grasping squid, with smooth surfaces that wouldn't damage the soft flesh. Still others appeared to have been bottom feeders, with teeth and jaw mechanics suited for crunching through shellfish. The polycotylids, a family of plesiosaurs that appeared in the Cretaceous, represent an interesting intermediate form. They had moderately short necks, longer than those of pliosaurs, but much shorter than the extreme elongation seen in elasmosaurids. Their heads were large and powerful, and some species show evidence of incredibly strong bite forces. These animals might have hunted a variety of prey, from fish to other marine reptiles, using a combination of speed and power to overwhelm their victims. Some plesiosaurs ventured into freshwater or brackish environments, showing the same ecological flexibility that we see in modern marine reptiles like crocodiles and sea turtles. Fossil plesiosaurs have been found in deposits that were clearly freshwater at the time they were laid down, suggesting these animals could tolerate or even prefer lower salinity waters. This would have given them access to prey species that were unavailable in the open ocean and might have allowed them to avoid competition with other marine predators. The social behavior of plesiosaurs remains largely mysterious, but tantalizing hints exist in the fossil record. Some fossil sites contain multiple individuals preserved together, which might indicate social aggregation. Whether these were family groups, hunting parties, or simply animals that happened to die in the same place is unclear. But the possibility that plesiosaurs had complex social structures, perhaps comparable to modern whales and dolphins, is intriguing and continues to drive research into their behavior. The sensory capabilities of plesiosaurs are also a subject of ongoing research. Their brain cases, preserved in some exceptional fossils, show that they had relatively large brains for reptiles, with well-developed regions associated with vision and coordination. Their eyes, while not as enormous as those of ichthyosaurs, were still quite large and would have provided good vision in the dimly lit waters where they hunted. Some species may have had additional senses, perhaps electroreception like modern sharks, though direct evidence for this is lacking. What we can say with certainty is that plesiosaurs were supremely adapted for their aquatic lifestyle. Every aspect of their anatomy, from their streamlined bodies to their powerful flippers, to their flexible necks, shows the result of millions of years of natural selection, refining them for life in the ocean. They were not transitional forms, awkwardly caught between land and sea, but fully realized marine animals, as comfortable in the water as fish, and far more successful than most. The end of the plesiosaurs came with the asteroid impact that closed the Cretaceous period. After surviving for so long, adapting to countless environmental changes, diversifying into dozens of species, they were eliminated in what was essentially an instant of geological time. The impact winter that followed the asteroid strike would have collapsed the marine food chain from the bottom up, and large predators like plesiosaurs, with their high food requirements, would have been among the first to starve. It's a sobering reminder that even the most successful groups, even the most perfectly adapted species, can be vulnerable to catastrophic change. Breathe deeply and let the tension flow out of your body as we move forward in time to the late Cretaceous, the final chapter in the story of the Mesozoic oceans. Around 98 million years ago, a new group of marine reptiles appeared, one that would rise to dominance with astonishing speed. These were the mosasaurs, and they were not distant relatives of dinosaurs, or plesiosaurs, or ichthyosaurs. They were lizards, true lizards, closely related to modern monitor lizards and snakes. The ancestors of mosasaurs were small, semi-aquatic lizards that lived along the shores of the shallow seas that had flooded across much of the continents during the Middle Cretaceous. They were creatures called aigialosaurs, no more than a meter long, with partially webbed feet and a lifestyle probably similar to modern marine iguanas. But something remarkable happened to these modest animals. Around 92 million years ago, a volcanic extinction event struck the oceans, one driven by massive underwater volcanic activity. This event wiped out the last of the ichthyosaurs and many of the pliosaurs, creating a sudden vacuum at the top of the marine food web. The mosasaurs seized this opportunity with spectacular success. In less than 25 million years, a geological eye blink, they evolved from small shore-dwelling lizards into some of the largest, most fearsome predators the oceans have ever known. Their limbs transformed completely into paddles, with webbed digits that allowed precise steering. Their bodies became more streamlined, with a tail that eventually developed a downward kink at the end to support a shark-like tail fluke, though this fluke was oriented vertically like a fish's tail rather than horizontally like a whale's. Their jaws evolved a special hinge that allowed the lower jaw to bow outward, expanding the gape so they could swallow enormous prey items whole. By the end of the Cretaceous, just before the asteroid impact that would end the age of dinosaurs, mosasaurs had diversified into an astonishing array of forms. There were small species barely 2 meters long, and gigantic species like Mosasaurus hoffmanni that stretched 17 meters from snout to tail and weighed as much as 15 tons. This particular species, the first mosasaur ever discovered and the one that gives the group its name, was found in a chalk quarry near Maastricht in the Netherlands in the 1700s. When naturalists first examined the massive skull, they thought it might be a crocodile, or perhaps a toothed whale. It was Georges Cuvier in 1808 who recognized it as something entirely different, a giant marine lizard unlike any living animal. This revolutionary insight helped establish the concept of extinction itself, the idea that species could disappear from the earth entirely. Mosasaurus was an apex predator of extraordinary power. Its skull alone was as long as a full-grown human, equipped with rows of conical teeth designed for gripping and tearing. But it also possessed a second set of teeth on the roof of its mouth, on the pterygoid bones, creating an extra trap that prevented struggling prey from escaping. Fossil evidence shows that Mosasaurus fed on an astonishing variety of prey. Paleontologists have found fish bones, shark teeth, cephalopod beaks, bird bones, and even the bones of other mosasaurs in the stomach regions of Mosasaurus fossils. These were generalist predators that would eat almost anything they could catch and overpower. Different mosasaurs evolved different feeding strategies. Some, like globidins, developed rounded bulbous teeth perfect for crushing shells. They fed on ammonites, the coiled shelled relatives of squid and octopi that were common in Cretaceous seas, crushing through the hard shells to get at the soft bodies inside. Others remained sleek fish eaters with narrow jaws full of sharp, pointed teeth. Still others grew to massive size and hunted the largest prey available, including plesiosaurs, large sharks, and even other mosasaurs. Recent discoveries have revealed that mosasaurs were not restricted to the oceans. Some species ventured into freshwater rivers, adapting to life in environments that were dramatically different from the marine realm. Pannoniasaurus, discovered in what is now Hungary, lived in fresh-water rivers on ancient islands. It had relatively robust limbs compared to its oceanic cousins, suggesting it might have hunted like a crocodile, lurking in the shallows and launching ambushes on unsuspecting prey. This discovery showed that mosasaur evolution was even more complex than previously thought, with different lineages independently evolving the adaptations needed for fully marine life. One of the most fascinating aspects of mosasaurs is how they regulated their body temperature. Unlike ichthyosaurs and plesiosaurs, which appear to have been fully warm-blooded, mosasaurs occupied a middle ground. They maintained a body temperature higher than the surrounding water, but that temperature would rise and fall slightly with changes in the ocean temperature. Some modern sharks use a similar strategy, called regional endothermy, where they keep certain parts of their bodies warm to improve muscle performance, while letting other parts remain cooler. This adaptation would have allowed mosasaurs to be powerful, active predators, while requiring less food than full endothermy would demand. Let yourself relax even more deeply now, feeling the gentle rhythm of your breathing as we consider the world these marine reptiles lived in. The Mesozoic oceans were profoundly different from our modern seas in ways that go beyond just the creatures living in them. The water was warmer, not just at the surface, but throughout the entire water column. Deep ocean temperatures during the Cretaceous may have reached 15 degrees Celsius or higher compared to the near freezing temperatures found in the deep ocean today. This meant that even the deepest parts of the ocean could support life in ways that modern abyssal zones cannot. To truly understand these ancient seas, we need to immerse ourselves in their world, to feel the warmth of the water, to sense the different rhythms of the currents, to appreciate how alien, yet how vital these oceans were. Picture yourself descending beneath the surface of a Jurassic Sea, perhaps 170 million years ago. The water that surrounds you is bathwater warm, even here at depths where modern oceans would be frigid and dark. Sunlight filters down through the clear water, creating shimmering columns of blue-green light that dance and sway with the movement of the surface far above. The chemistry of the seawater was different as well. At times during the Mesozoic, particularly during the Cretaceous, the oceans became stratified, with a warm, salty surface layer and a cooler, fresher layer below. This stratification could limit the mixing of oxygen into the deep waters, creating what scientists call oceanic anoxic events, times when the deep oceans became starved of oxygen and accumulated organic rich sediments that would eventually become some of the world's richest oil deposits. These events had profound effects on marine life, creating dead zones where nothing could survive, but also, paradoxically, times when surface productivity reached extraordinary levels as nutrients accumulated in the upper layers. The temperature distribution in Mesozoic oceans was far more uniform than it is today. The difference between equatorial and polar waters was much smaller, perhaps only 10 or 15 degrees Celsius compared to the 30-degree or greater difference we see in modern oceans. This meant that marine reptiles could inhabit a much wider range of latitudes without encountering water too cold for their metabolism. Plesiosaurs fossils have been found in rocks deposited in ancient polar seas, where they would have experienced months of continuous daylight in summer and months of darkness in winter, yet where the water remained temperate rather than freezing. This warmth extended even to the polar regions because there were no ice caps to chill the water. The Arctic and Antarctic were ice-free throughout most of the Mesozoic, covered instead by forests of conifers, ferns, and later flowering plants. Rain fell on these polar forests, running off into rivers and eventually into the ocean, bringing nutrients and fresh water that supported rich ecosystems along the coasts. Marine reptiles could hunt in these high-latitude waters, pursuing fish and squid that thrived in the long summer days of continuous sunlight. The sea levels fluctuated dramatically throughout the Mesozoic, rising and falling by hundreds of meters. During the high stands, shallow seas flooded across the continents, creating vast epiric seas that were perfect habitats for marine reptiles. The Western Interior Seaway, for example, stretched from the Gulf of Mexico all the way to the Arctic Ocean during the late Cretaceous, splitting North America in two. This shallow, warm inland sea was home to countless mosasaurs, plesiosaurs, and other marine creatures. Today, fossils of these ocean-going reptiles can be found in places like Kansas and South Dakota, hundreds of miles from the nearest ocean, testament to how different the geography of the Cretaceous was from our world. These inland seas were not deep like modern oceans. They averaged only a few hundred meters in depth, shallow enough that storms could churn sediments from the bottom, and that seasonal changes could affect the entire water column. The warmth and shallowness meant that productivity was high, with abundant plankton supporting large populations of fish, which in turn supported the marine reptiles. The seabed would have been carpeted with oysters, clams, and other shellfish, creating feast opportunities for specialized feeders like the placodonts and shell-crushing mosasaurs. The continents themselves were moving, pulled apart by the forces of plate tectonics. As Pangaea fragmented and the Atlantic Ocean widened, ocean currents changed their patterns. New seaways opened between land masses, allowing water to flow in different directions, redistributing heat around the planet. The breakup of the supercontinent was driven by volcanic activity along spreading ocean ridges, and this volcanism released enormous quantities of carbon dioxide into the atmosphere, contributing to the greenhouse climate of the Mesozoic. The length of mid-ocean ridges, the underwater mountain ranges where new seafloor is created, doubled from the Triassic to the early Cretaceous. This increased volcanic activity not only produced carbon dioxide, but also displaced water, contributing to the rising sea levels that flooded the continents. The opening of new ocean basins created new habitats for marine reptiles to colonize, new opportunities for speciation and adaptation. The climate of the Mesozoic was largely a greenhouse climate, with no permanent polar ice caps. Carbon dioxide levels were significantly higher than they are today, though they fluctuated considerably over the course of the era. During the warmest periods, atmospheric carbon dioxide might have been 4 or more times higher than pre-industrial levels, creating a world where temperatures were remarkably uniform from pole to pole. This greenhouse climate meant that temperature differences between the equator and the poles were much less extreme than they are now. Forests grew in polar regions, and marine reptiles swam in waters that were far warmer than anything we would expect to find at such high latitudes today. But these warm conditions were not constant throughout the entire Mesozoic. Recent research has revealed that parts of the Jurassic and Cretaceous experienced cooler intervals, times when sea surface temperatures dropped and conditions became more seasonal. During the early Jurassic, for instance, evidence suggests that sea surface temperatures in some regions were close to freezing, at least seasonally. Marine reptiles living during these periods would have needed to cope with greater temperature variation and the presence of features like blubber insulation in some fossils suggests that they were well equipped to do so. The circulation patterns of Mesozoic oceans were fundamentally different from those we see today. Modern ocean circulation is driven largely by the formation of cold, dense water at the poles, which sinks and flows toward the equator along the ocean floor, creating a global conveyor belt that redistributes heat. But in the Mesozoic, with no ice caps to create this cold water, circulation was driven by different mechanisms. Warm, salty water formed in shallow tropical seas through intense evaporation. This dense water would sink and flow into the deeper ocean, creating warm bottom currents rather than the cold ones we have today. This meant that the deep ocean in the Mesozoic was a very different environment from what we see now. Instead of the cold, stable, low oxygen conditions of modern deep seas, Mesozoic deep waters might have been warmer, more variable, and at times better oxygenated. This would have allowed deep-dwelling organisms to flourish in ways that modern deep-sea creatures cannot, though at other times, particularly during oceanic anoxic events, the deep ocean might have been nearly lifeless. The surface currents also follow different patterns, with the continents arranged differently and no polar ice to create the temperature gradients that drive modern currents. The flow of water around the globe would have taken different routes. The Tethys Sea, a vast tropical ocean that existed between the northern and southern portions of the fragmenting Pangaea, created a circum-equatorial current that distributed heat and nutrients around the globe. This current had no modern equivalent and would have created unique oceanographic conditions that marine reptiles adapted to. Tidal patterns would have been different as well, though for a different reason. The moon was closer to Earth during the Mesozoic, which meant that tidal forces were stronger. Days were also shorter, only about 23 hours long in the Jurassic, gradually lengthening to about 23.5 hours by the end of the Cretaceous. These shorter days and stronger tides would have created more vigorous mixing of coastal waters. potentially increasing productivity in near-shore environments where many marine reptiles hunted. The seasonal patterns in Mesozoic oceans were less pronounced in tropical regions, but more extreme at high latitudes than today. The uniform warmth meant that tropical seas didn't experience the temperature fluctuations that drive modern monsoons and seasonal upwelling. But at high latitudes, the extreme variation in daylight, from 24-hour daylight in summer to 24-hour darkness in winter, would have created strong seasonal cycles in productivity. Marine reptiles living in these regions might have migrated to follow food sources, much as modern whales do, or they might have adapted to feast during the productive summer months and endure leaner times in winter. Storm systems in the Mesozoic might have been more intense than modern storms due to the greater temperature uniformity. Without the strong temperature gradient between equator and poles that helps to organize modern weather systems, Mesozoic storms might have been more chaotic and less predictable. The shallow inland seas would have been particularly vulnerable to these storms, which could churn up sediments, redistribute nutrients, and create challenging conditions for marine life. The productivity of Mesozoic oceans varied considerably over space and time. Coastal regions and shallow seas were generally highly productive, with abundant plankton supporting complex food webs. Upwelling zones, where deep nutrient-rich water rose to the surface, would have created oases of productivity in otherwise less fertile regions. The open ocean might have been less productive than coastal waters, though the warm temperatures throughout the water column might have allowed greater vertical distribution of plankton than we see in modern tropical oceans. During oceanic anoxic events, surface productivity could reach extraordinary levels as nutrients accumulated in the upper water column. These events created a paradox. The surface waters were incredibly fertile, teeming with plankton and the creatures that fed on them, while the deeper waters were starved of oxygen and nearly lifeless. Marine reptiles, as air breathers that spent most of their time near the surface, would have been well positioned to take advantage of these highly productive surface conditions. The composition of plankton communities changed dramatically over the course of the Mesozoic. In the Triassic and early Jurassic, plankton communities were dominated by green algae and other organisms with simple cell structures. But during the Jurassic, and especially the Cretaceous, new groups of plankton evolved and became dominant. Coccolithophores, tiny algae covered in calcium carbonate plates, became incredibly abundant, sometimes forming blooms that covered vast areas of ocean. When these organisms died, their plates settled to the seafloor, accumulating over millions of years to form the thick chalk deposits that give the Cretaceous period its name. Diatoms, microscopic algae with intricate silica shells, also became important during the Cretaceous, adding another major group to the plankton community. These organisms were remarkably efficient at photosynthesis and could quickly take advantage of nutrient-rich conditions. The evolution of these new plankton groups had cascading effects throughout the marine ecosystem, changing the nature of the food webs that supported everything from small fish to giant marine reptiles. The chemistry of seawater changed in other ways as well. The ratio of different isotopes of carbon and oxygen fluctuated in response to changes in volcanic activity, weathering rates on land, and the burial of organic carbon in ocean sediments. These changes left a record in the shells of marine organisms, a record that modern scientists can read to reconstruct ancient ocean conditions. Through careful isotopic analysis, researchers have been able to determine ocean temperatures, salinity, and even the rate of primary productivity at different times during the Mesozoic. Calcium carbonate saturation, which affects how easily organisms can build shells and skeletons, also varied. During times of high volcanic activity and high atmospheric carbon dioxide, more carbon dioxide dissolved into the ocean, making the water more acidic and reducing calcium carbonate saturation. This would have made it harder for organisms with calcium carbonate shells or skeletons to build and maintain their hard parts. Yet marine ecosystems proved remarkably resilient, with many organisms adapting to these challenging conditions. The presence of islands and archipelagos added complexity to Mesozoic ocean geography. As Pangaea fragmented, it didn't simply split into the continents we know today. Instead, it broke into countless smaller pieces, creating chains of volcanic islands, isolated continental fragments, and shallow seas dotted with reefs. These complex coastlines created innumerable ecological niches, places where specialized marine reptiles could evolve and thrive. Some species might have been restricted to particular island chains or shallow seas, while others ranged widely across open ocean basins. Volcanic islands, in particular, would have been important features of Mesozoic oceans. Underwater volcanoes created new islands, which were then colonized by terrestrial life and surrounded by rich marine ecosystems. The fertile waters around these islands, enriched by volcanic nutrients, would have attracted fish and other prey, which in turn would have drawn marine reptile predators. Some marine reptiles might have used remote islands as rookeries or haul-out sites, though direct evidence for this is lacking. The seafloor itself was a dynamic environment. In shallow seas, the bottom was often covered with shell beds, accumulations of oysters, clams, and other bivalves that created three-dimensional habitats. These shell beds supported diverse communities of invertebrates, fish, and other organisms. Some marine reptiles, particularly the placoodonts and some plesiosaurs, specialized in feeding on these seafloor communities, crushing shells, or picking off the organisms that lived among them. In deeper waters, the seafloor was usually covered with fine sediments that settled slowly from above. These sediments accumulated organic matter, the dead bodies of plankton and other organisms that sank from the productive surface waters. During normal times, burrowing organisms would mix these sediments and consume the organic matter, oxygenating the seafloor and preventing the accumulation of undecayed material. But during oceanic anoxic events, the lack of oxygen allowed organic matter to accumulate, creating the dark, organic-rich layers that would eventually become oil source rocks. Hydrothermal vents, cracks in the seafloor where superheated water rich in minerals emerges, existed in Mesozoic oceans just as they do today. These vents supported unique ecosystems based not on photosynthesis, but on chemosynthesis, where bacteria extracted energy from chemical compounds in the vent fluids. While we have no direct evidence that marine reptiles visited these vents, the rich communities of fish and invertebrates that modern vents support suggest that ancient vents might have attracted some deep diving predators. Seeps, where methane or oil seeps slowly from the seafloor were another unusual habitat. These seeps also supported chemosynthetic communities and would have created localized oases of life on an otherwise less productive seafloor. The methane from some of these seeps might have occasionally formed massive bubbles that rose explosively to the surface, creating temporary disturbances that would have been noticed by any marine reptiles in the vicinity. Storms and other extreme weather events would have periodically disrupted the normally placid conditions of Mesozoic seas. Hurricanes, or their Mesozoic equivalents, would have churned up surface waters, mixed nutrients from depth, and created challenging conditions for marine life. Marine reptiles, as air breathers, would have needed to surface regularly even in the roughest seas, and storms might have been times of particular danger. However, their streamlined bodies and powerful swimming abilities would have allowed them to dive deep to escape the worst of the surface turbulence. The chemistry of the seawater was different as well. At times during the Mesozoic, particularly during the Cretaceous, the oceans became stratified, with a warm, salty surface layer and a cooler, fresher layer below. This stratification could limit the mixing of oxygen into the deep waters, creating what scientists call oceanic anoxic events, times when the deep oceans became starved of oxygen and accumulated organic-rich sediments that would eventually become some of the world's richest oil deposits. The sea levels fluctuated dramatically throughout the Mesozoic, rising and falling by hundreds of meters. During the high stands, shallow seas flooded across the continents, creating vast epiric seas that were perfect habitats for marine reptiles. The Western Interior Seaway, for example, stretched from the Gulf of Mexico all the way to the Arctic Ocean, splitting North America in two. This shallow, warm inland sea was home to countless mosasaurs, plesiosaurs, and other marine creatures. Today, fossils of these ocean-going reptiles can be found in places like Kansas and South Dakota, hundreds of miles from the nearest ocean, testament to how different the geography of the Cretaceous was from our world. The continents themselves were moving, pulled apart by the forces of plate tectonics. As Pangaea fragmented and the Atlantic Ocean widened, ocean currents changed their patterns. New seaways opened between land masses, allowing water to flow in different directions, redistributing heat around the planet. The climate of the Mesozoic was largely a greenhouse climate, with no permanent polar ice caps. Carbon dioxide levels were significantly higher than they are today, though they fluctuated considerably over the course of the era. This greenhouse climate meant that temperature differences between the equator and the poles were much less extreme than they are now. Forests grew in polar regions, and marine reptiles swam in waters that were far warmer than anything we would expect to find at such high latitudes today. But these warm conditions were not constant throughout the entire Mesozoic. Recent research has revealed that parts of the Jurassic and Cretaceous experienced cooler intervals, times when sea surface temperatures dropped and conditions became more seasonal. Marine reptiles living during these periods would have needed to cope with greater temperature variation, and the presence of features like blubber insulation in some fossils suggests that they were well equipped to do so. As you continue to breathe slowly and deeply, letting yourself drift into an even more relaxed state, imagine the complexity of the food webs in these ancient oceans. At the base, were microscopic organisms, plankton that drifted in the currents, photosynthesizing in the sunlit surface waters, or feeding on detritus that rained down from above. These included coccolithophores, tiny algae that secreted button-like calcium carbonate plates around their cells, and diatoms, silica-shelled microscopic plants. When these organisms died, their shells accumulated on the seafloor, eventually forming the chalk and chert deposits that we find today. The plankton formed the foundation of everything else, converting sunlight and dissolved nutrients into living biomass that could be consumed by larger organisms. In a single drop of Mesozoic seawater, there might have been thousands of individual plankton cells, each one carrying out photosynthesis, absorbing carbon dioxide and releasing oxygen. During blooms, when conditions were perfect, plankton could become so abundant that they colored the water, creating vast patches of green or brown ocean visible from space, if there had been anyone in space to see them. Feeding on the plankton were countless small fish and invertebrates, ammonites, those beautiful coiled-shelled cephalopods, were incredibly diverse in the Mesozoic, with species sporting shells that were coiled, straight, hooked, or twisted into bizarre knotted shapes. These creatures were relatives of modern nautilus, with soft bodies protected by hard shells divided into chambers. As an ammonite grew, it would add new chambers to its shell, maintaining buoyancy by controlling the gas and liquid content of the older chambers behind it. Ammonites came in an astonishing range of sizes. Some were no bigger than a coin, delicate little creatures that fed on microscopic prey in the surface waters. Others grew to enormous dimensions, with shells measuring over 2 meters in diameter, making them among the largest invertebrates that have ever lived. These giants likely lived in deeper waters, their shells helping them maintain neutral buoyancy as they drifted through the oceanic twilight zone, using their tentacles to capture passing prey. The shells of ammonites were works of art, covered in ridges, spines, and ornamentations that varied from species to species. Scientists still debate the function of these elaborate decorations. Some might have provided structural strength, others might have improved swimming efficiency, and still others might have served as defenses against predators, or as recognition signals for members of the same species. Whatever their purpose, these beautiful shells have left us a rich fossil record that helps us understand the evolution and diversity of Mesozoic seas. Belemnites, extinct relatives of modern squid, were equally common, their bullet-shaped internal shells preserved in enormous numbers in some fossil beds. Unlike ammonites, which wore their shells on the outside, belemnites had internal shells called guards that provided structural support and perhaps served as ballast to help control buoyancy. The soft bodies of belemnites were streamlined and fast-moving, equipped with tentacles for capturing prey and jet propulsion for rapid escape from predators. These cephalopods were fast-moving predators in their own right, feeding on small fish and crustaceans, but they also formed a crucial food source for larger animals. Marine reptiles of all kinds hunted ammonites and belemnites, and fossil evidence provides direct proof of this relationship. Ammonite shells have been found with bite marks that match the teeth of marine reptiles, some showing the characteristic crushing damage of mosasaur jaws, others showing the puncture marks of plesiosaur teeth. Some ammonite shells show evidence of repeated attacks, where the creature survived one encounter and began to repair its damaged shell before falling victim to another predator. The fish of the Mesozoic seas were different from most modern fish, though some groups would be recognizable. Sharks prowled these waters, ancient lineages that had been in the oceans far longer than any of the marine reptiles. These sharks were not identical to modern species, though they filled similar ecological roles. Some were small, nimble hunters of fish and invertebrates. Others grew to impressive sizes, becoming predators capable of taking on marine reptiles. One group of Mesozoic sharks, the hybodontids, were particularly diverse and successful. These sharks had features not seen in modern sharks, including spine on their dorsal fins and crushing teeth in the backs of their jaws for breaking shells. They occupied a variety of ecological niches, from bottom-dwelling shell crushers to active mid-water predators. The hybodontids survived from the late Paleozoic through most of the Mesozoic, finally going extinct at the end of the Cretaceous, along with the marine reptiles and so many other groups. Bony fish of various kinds filled countless ecological niches, from tiny sardine-like schooling fish to massive predatory forms. Some of these fish would be completely alien to modern eyes, with bizarre body plans and unusual adaptations. Others would look remarkably familiar, early members of groups that still exist today. Sturgeon, for instance, have an ancient lineage extending back into the Mesozoic, and Mesozoic sturgeon would have looked much like their modern descendants. Bottom feeders with whisker-like barbels for sensing prey in the sediment. Pachycormids were a group of large, predatory fish that were particularly important in Jurassic seas. Some species reached lengths of several meters and had powerful jaws filled with sharp teeth. These fish were fast swimmers, built somewhat like modern tuna or billfish, and they would have been formidable predators, competing with marine reptiles for prey. Other pachycormids evolved in the opposite direction, becoming filter feeders that strained plankton from the water, with specialized gill rakers, much like modern basking sharks do. The oceans also contained representatives of more archaic fish groups that have since disappeared or become restricted to specialized environments. Coelacanths, which today survive as rare deep-water relics, were diverse and relatively common in Mesozoic seas. Lungfish, now restricted to freshwater, had marine representatives during parts of the Mesozoic. These ancient fish groups remind us that the Mesozoic was a time of transition, when older forms still persisted alongside newer groups that were beginning their rise to dominance. Crustaceans played important roles in Mesozoic marine ecosystems, though they are less well represented in the fossil record than shelled organisms. Shrimp, lobsters, and crabs all existed during the Mesozoic, filling various ecological niches. Some were bottom dwellers, scavenging on dead material that settled to the seafloor. Others were active swimmers, hunting smaller prey or grazing on algae. The evolution of crabs during the Jurassic and Cretaceous had significant impacts on other marine organisms, as crabs became increasingly sophisticated at cracking open shells, creating new selective pressures for animals with protective armor. Smaller invertebrates carpeted the seafloor and floated in the water column. Sea urchins and their relatives grazed on algae and scavenged on detritus. brittle stars and sea stars prowled the bottom, hunting for small prey or consuming dead material. Worms of various kinds burrowed through sediments or built tubes on hard surfaces. These smaller organisms might seem insignificant compared to the giant marine reptiles, but they were essential to ecosystem function, recycling nutrients and providing food for larger animals. Corals built reefs in shallow tropical waters, just as they do today, though Mesozoic reefs were constructed by different coral species than modern reefs. These reefs created complex three-dimensional habitats that supported incredible diversity. Fish sheltered among the coral branches, invertebrates hid in crevices, and larger predators patrolled the reef edges looking for unwary prey. Some marine reptiles might have hunted around these reefs, their maneuverable bodies allowing them to navigate the complex terrain. Bivalves, the group that includes clams, oysters, and mussels, were extraordinarily diverse and abundant in Mesozoic seas. They filtered plankton from the water, accumulating in vast beds that carpeted the seafloor in some regions. Certain fossil deposits contain layer upon layer of oyster shells, meters thick, testament to the incredible productivity of these animals. These shell beds provided habitat for other organisms and food for specialized predators. The placodonts of the Triassic built their entire lifestyle around crushing these shells, and later shell-crushing mosasaurs did the same. Some bivalves evolved remarkable adaptations during the Mesozoic. The rudists, a now extinct group, evolved into forms that looked more like corals than clams, with one shell forming a cone-shaped base attached to the substrate and the other forming a lid on top. These rudists built extensive reefs in tropical shallow waters during the Cretaceous, creating habitats that were different from both modern coral reefs and modern oyster reefs. When the rudists went extinct at the end of the Cretaceous, reef ecosystems were fundamentally changed. Snails, both shelled and shell-less forms, were diverse and important. Some grazed on algae, scraping it from rocks with their rough radulae. Others were predators, drilling holes in the shells of other mollusks to access the soft flesh inside. Still others were scavengers, feeding on dead material. The fossil record preserves beautiful shells from Mesozoic snails, some coiled in spirals, others shaped like towers or cones, decorated with spines, ridges, and intricate patterns. Squid, the shell-less relatives of ammonites and modern cuttlefish, were present in Mesozoic seas as well, though they left fewer fossils than their shelled cousins, their soft bodies rarely preserved, but occasionally exceptional fossil sites capture their outlines, showing us animals that would look quite familiar to anyone who has seen modern squid. They were fast, intelligent predators, capable of rapid color changes and jet-propelled escapes. Marine reptiles certainly hunted them, as hooks from squid tentacles are common in fossil stomach contents. The octopuses, most intelligent of all invertebrates, also existed during the Mesozoic, though direct fossil evidence is scarce due to their entirely soft bodies. We know they were present because some ammonite shells show distinctive damage patterns consistent with octopus predation. Modern octopuses attack shelled prey by drilling a hole through the shell or by pulling the animal out with their powerful arms and beak. Similar damage on Mesozoic shells suggests octopuses were employing the same tactics millions of years ago. Jellyfish and other gelatinous organisms drifted through Mesozoic waters as they do today, though they left almost no fossil record. We know they were there because they are such a fundamental part of marine ecosystems, consuming plankton and smaller fish, while providing food for larger predators. Some modern marine turtles feed extensively on jellyfish, and it's possible that some Mesozoic marine reptiles did the same, though proving this from fossil evidence is extremely difficult. The ecology of these food webs was complex and dynamic. Energy flowed from the sun to plankton, from plankton to small herbivores and filter feeders, from those organisms to small predators, and then up through layers of increasingly larger predators until finally reaching the top predators, the largest sharks, bony fish, and marine reptiles. But the flow wasn't unidirectional. Dead organisms at every level sank to provide food for bottom-dwelling scavengers. Waste products were recycled by bacteria and other decomposers. Nutrients were mixed vertically by currents and upwelling, supporting new growth of plankton. Marine reptiles fit into this web at multiple levels. Small species fed on fish and invertebrates. Medium-sized species might have specialized on particular prey types, and the largest species were apex predators that hunted whatever they could catch. Some species might have shifted their diet as they grew, starting as hunters of small prey when young and graduating to larger prey as adults. This ontogenetic dietary shift is seen in many modern predators and probably occurred in marine reptiles as well. The competition between different groups of marine predators would have been intense. Marine reptiles competed with large sharks and predatory fish for prey. At times, one group might have had the advantage, perhaps through superior swimming ability or more efficient metabolism. At other times, conditions might have favored their competitors. The fossil record shows fluctuations in the diversity and abundance of different groups over time, possibly reflecting these competitive interactions. But competition wasn't the only relationship between species. Smaller fish might have cleaned parasites from marine reptiles, as cleaner fish do for modern sharks and manta rays. Remoras, fish that attach to large animals with sucker-like organs, might have hitched rides on marine reptiles, feeding on scraps from the reptile's meals or on parasites on its skin. These symbiotic relationships are nearly impossible to prove from fossils, but they are so common in modern marine ecosystems that they very likely existed in the Mesozoic as well. Predation pressures shape the evolution of prey species in fascinating ways. Ammonites with thicker shells or more spines might have been harder to crack or swallow. Fish that schooled together might have confused predators, or made it harder for a predator to target a single individual. Squid that could change color rapidly might have been able to startle predators or blend into the background. These defensive adaptations, in turn, drove the evolution of counter-adaptations in predators, creating an evolutionary arms race that played out over millions of years. The seasonal cycles affected food web dynamics significantly, especially at higher latitudes. During the long summer days at polar latitudes, photosynthesis could occur around the clock, leading to explosions of plankton growth. This abundance rippled up through the food chain, supporting dense populations of fish, which attracted marine reptiles. During winter, with months of darkness, primary productivity crashed, and many animals might have migrated to lower latitudes or survived on stored fat reserves. Migrations of prey species would have drawn marine reptile predators. If fish migrated to spawning grounds, marine reptiles might have followed, taking advantage of the concentrated food source. If squid populations moved with seasonal changes in ocean temperature or productivity, their predators would have tracked these movements. The fossil record sometimes hints at these patterns, with marine reptile fossils concentrated in areas that might have been migration routes or feeding grounds. Upwelling zones, where deep, nutrient-rich water rose to the surface, would have been hot spots of productivity and predator activity. These zones supported dense concentrations of plankton, which attracted fish and other prey, which in turn attracted marine reptile predators. Modern upwelling zones are among the most productive parts of the ocean, and Mesozoic upwelling zones probably function similarly, creating oases of abundance in otherwise less fertile waters. The food webs were not static, but changed over the course of the Mesozoic, as new groups evolved and old groups went extinct. The replacement of ichthyosaurs by mosasaurs in the mid-Cretaceous, for instance, would have reorganized predator-prey relationships throughout the marine ecosystem. The evolution of new types of fish, crustaceans, and mollusks created new opportunities for predators to exploit. The appearance of flowering plants on land during the Cretaceous led to increased nutrient runoff into coastal waters, potentially boosting coastal productivity and supporting larger populations of marine life. The fish of the Mesozoic seas were different from most modern fish, though some groups would be recognizable. Sharks prowled these waters, ancient lineages that had been in the oceans far longer than any of the marine reptiles. Bony fish of various kinds filled countless ecological niches, from tiny sardine-like schooling fish to massive predatory forms. And then, of course, there were the marine reptiles themselves, operating at multiple levels of the food web, depending on their size and specialization. This complex ecosystem was not static, but constantly evolving, shifting in response to changes in climate, sea level, and the evolution of new species. The extinction at the end of the Triassic reset the system, eliminating many groups and allowing others to diversify into the empty niches. The extinction event in the Middle Cretaceous did the same, removing the ichthyosaurs and many pliosaurs, and paving the way for the mosasaur radiation. And finally, at the end of the Cretaceous, the entire system would be swept away by the catastrophe that ended the Mesozoic Era. 66 million years ago, an asteroid perhaps 10 kilometers in diameter slammed into what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear weapons, triggering earthquakes, tsunamis, and wildfires. Dust and debris were hurled into the atmosphere, blocking out the sun for months or years. The global climate plunged into impact winter. Photosynthesis shut down across much of the planet, and food chains collapsed. In the oceans, the destruction was catastrophic. The marine ecosystem, which had been complex and productive right up until the moment of impact, disintegrated. The plankton communities crashed, eliminating the base of the food web. Without plankton to feed on, the small fish and invertebrates died. Without those prey species, the larger predators starved. The mosasaurs, which had been at the height of their diversity and success just before the impact, vanished entirely. The plesiosaurs, which had ruled the seas for over 140 million years, disappeared as well. The marine reptiles, which had been such a dominant presence in Mesozoic oceans, were gone. Only a few lineages survived. Sea turtles made it through, though greatly reduced in diversity. Marine crocodiles, which had existed alongside the mosasaurs and plesiosaurs, survived in reduced numbers. But the great age of marine reptiles was over. The oceans were left strangely empty, their top predator niches vacant. It would be millions of years before mammals began to venture into these empty seas, following the same evolutionary trajectory that the reptiles had followed before them. The whales and dolphins we know today are the descendants of those mammalian pioneers, and remarkably, they evolved body shapes and lifestyles startlingly similar to the ichthyosaurs that had preceded them by 150 million years. As you breathe slowly and peacefully, reflecting on this vast sweep of time and change, consider what the story of the Mesozoic marine reptiles teaches us. These animals show us evolution's extraordinary creativity, its ability to take creatures adapted for one environment and transform them, over time, into beings perfectly suited for something completely different. The ichthyosaurs went from being land-dwelling reptiles to becoming more dolphin-like than the mammals that would later evolve into dolphins. The plesiosaurs developed a swimming style that has never been repeated in the entire history of life on Earth. The mosasaurs went from small shore-dwelling lizards to massive ocean predators in less than 30 million years. But this story also shows us the fragility of even the most successful groups. For all their dominance, for all their perfect adaptations, the marine reptiles were vulnerable to the kind of catastrophic change that came at the end of the Cretaceous. The same asteroid that killed the last non-avian dinosaurs also eliminated every large marine reptile. The complexity they represented, the accumulated adaptations of tens of millions of years of evolution, vanished in what was, geologically speaking, an instant. Yet the oceans recovered. Life proved resilient, as it always has. New groups arose to fill the empty niches. The seas today are as full of life as they were in the Mesozoic, though that life takes different forms now, and preserved in the rocks, in limestone and shale and chalk deposits around the world, we find the remains of those ancient ocean dwellers, their fossilized bones telling us stories of a world that existed long before humans, long before mammals became dominant, in an age when reptiles ruled not just the land, but the sea as well. Let yourself sink into complete relaxation now, your breathing slow and steady, your mind at peace. Picture one final scene from the Mesozoic oceans. It's a warm evening in the late Cretaceous, perhaps 67 million years ago. The sun is setting over a vast, shallow sea, painting the water in shades of orange and gold. Below the surface, a mosasaur glides through the depths, its powerful tail sweeping back and forth, propelling it forward with effortless grace. In the distance, a long-necked plesiosaur rises to the surface to breathe, its small head breaking through the waves before it descends again into the blue. Schools of fish shimmer in the fading light, and somewhere far below, in the cooler depths, Sharks patrol their territories as they have for hundreds of millions of years. This is a world at peace, a world in balance, a world that has existed in various forms for nearly 200 million years. The creatures living in it have no knowledge that their time is nearly over, that within 1 million years their lineages will be extinct. They simply live, hunt, breed, and die, following patterns that have been refined over countless generations, and in doing so, they create the fossil record that will one day allow creatures they could never imagine, creatures called humans, to reconstruct their story and marvel at what they were. The Mesozoic marine reptiles lived in oceans we can never visit, in climates we can never experience directly. But through the patient work of paleontologists, through careful study of fossilized bones and ancient rocks, we can reconstruct their world with increasing accuracy. We can understand how they swam, what they ate, how they reproduced, even what color some of them might have been. Each new discovery adds detail to the picture, brings these animals back to life in our minds, if not in physical reality. The story of how we came to know these creatures is itself a fascinating journey through the history of science. The first marine reptile fossils were discovered long before anyone understood what they were. In some cases, people have been finding these fossils for centuries, interpreting them as the bones of giants, dragons, or other mythical creatures. It wasn't until the late 18th and early 19th centuries that scientists began to recognize them for what they truly were: extinct animals unlike anything alive today. One of the most important early sites for marine reptile fossils was the coastal town of Lyme Regis in Dorset, England. The cliffs there are made of rocks from the early Jurassic, laid down in shallow seas around 200 million years ago. These rocks have yielded countless fossils, from delicate ammonites to massive marine reptile skeletons. The person most associated with these discoveries is Mary Anning, one of the most important fossil collectors in history, and a pioneer in a field that was, at the time, dominated by wealthy men. Mary Anning was born in 1799 into a working-class family in Lyme Regis. Her father was a carpenter who supplemented his income by collecting fossils from the beaches and cliffs to sell to tourists. Mary learned the trade from him, developing an uncanny ability to spot fossils in the rock and extract them without damage. When her father died in 1810, leaving the family in poverty, Mary took up fossil collecting as her profession, becoming one of the most skilled and knowledgeable fossil hunters of her time. In 1811, when she was just 12 years old, Mary Anning discovered the first complete ichthyosaur skeleton ever found. It was a spectacular specimen, perfectly preserved with every bone in place, and it caused a sensation when it was described to the scientific community. This was followed by more discoveries over the years, including the first complete plesiosaur skeleton in 1823, and numerous other important fossils. Mary Anning's discoveries helped to establish the reality of extinction and contributed enormously to our understanding of prehistoric life. The ichthyosaur she found, eventually identified as Temnodontosaurus plateodon, showed features that amazed the scientists who studied it. The enormous eyes were immediately apparent, as was the streamlined body shape. At first, scientists weren't sure how to interpret the skeleton. Some thought it might be a fish, others a crocodile. It took years of study and comparison with other fossils before its true nature as a marine reptile became clear. Mary Anning worked in difficult and dangerous conditions. The cliffs at Lyme Regis are unstable, prone to landslides, especially after heavy rains. Anning herself nearly died in a landslide that killed her dog, but she continued her work, driven by necessity and by a genuine passion for understanding these ancient creatures. Despite her enormous contributions, she received little recognition during her lifetime. As a woman without formal education, she was excluded from the scientific societies of the day and rarely credited in the scientific papers that were based on her discoveries. Today, Mary Anning is recognized as one of the most important figures in the history of paleontology, and her story reminds us that scientific knowledge often comes from unexpected sources. The fossils she found are now in museums around the world, still being studied and still revealing new insights into the Mesozoic seas. The cliffs at Lyme Regis continue to yield fossils, as erosion gradually exposes new specimens that have been locked in the rock for 200 million years. Germany's Holzmaden quarries represent another world-famous site for marine reptile fossils, particularly ichthyosaurs. The rocks here are slightly younger than those at Lyme Regis, from the later part of the early Jurassic, and they preserve marine life in extraordinary detail. The fine-grained limestone captures not just bones, but also soft tissue outlines, showing us the shape of bodies, the presence of fins, even in some cases the last meals still in the stomach. The Holzmaden fossils revealed features of ichthyosaurs that no one had suspected from earlier finds. The presence of a dorsal fin, for instance, was first confirmed here, from fossils that showed the outline of the fin preserved as a dark organic film around the skeleton. The tail fluke, which had been debated for decades, was finally proven to exist when fossils showed its shape clearly, and the pregnant females with their developing young provided conclusive evidence that ichthyosaurs gave birth to live young in the water. The preservation at Holzmaden is exceptional because of the particular conditions that existed there during the early Jurassic. The seafloor was anoxic, lacking oxygen, which meant that scavengers couldn't survive there to disturb dead bodies. When an ichthyosaur died and sank to the bottom, it would lie there undisturbed, slowly being buried in fine mud that settled from above. This mud protected the body from decay, and eventual preserved even the softest tissues as carbonaceous films. Across the Atlantic, the western interior seaway of North America has yielded enormous numbers of marine reptile fossils, particularly from the late Cretaceous. Places like Kansas, which is now about as far from the ocean as you can get in North America, were once underwater, and their rocks contain spectacular fossils of mosasaurs, plesiosaurs, and other marine life. The Smoky Hill Chalk of Kansas, in particular, has produced some of the best preserved mosasaur fossils ever found. These fossils have taught us an enormous amount about mosasaur biology and ecology. We know from Kansas fossils what mosasaurs ate because their stomach contents are often preserved. We know they gave birth to live young from fossils showing pregnant females. We know they sometimes fought each other from fossils showing healed bite marks. We even know something about their skin texture and coloration from rare fossils that preserve skin impressions. The discovery and excavation of these fossils is itself an adventure. Many are found in remote areas, requiring long expeditions to reach. Once located, a fossil must be carefully excavated, a process that can take days, weeks, or even months, depending on the size of the specimen and the hardness of the surrounding rock. The fossil must be protected as it's removed, often by covering it in plaster jackets that keep the bones from breaking apart. Then it must be transported back to a museum or laboratory where the real work of preparation begins. Preparation of fossils is a slow, meticulous process. The rock surrounding the bones, called matrix, must be carefully removed using tools ranging from hammers and chisels to dental picks and even needles, all while ensuring that the fossil itself isn't damaged. Some fossils take years to prepare fully, but the result is worth the effort, a specimen that can be studied, displayed, and preserved for future generations. Modern techniques have revolutionized how we study fossil marine reptiles. CT scanning allows us to see inside bones without damaging them, revealing internal structures like the brain cavity, the inner ear, and the blood vessel channels. This provides information about sensory capabilities, intelligence, and metabolism that would be impossible to obtain otherwise. Some specimens have been scanned and then digitally reconstructed, creating three-dimensional models that can be manipulated and studied in ways that would be impossible with the actual fossils. Chemical analysis of fossil bones can tell us about diet, habitat, and even body temperature. Isotopic analysis, which measures the ratios of different isotopes of elements like oxygen and carbon in the bone, provides information about the temperature of the water the animal lived in and what it was eating. This technique has been crucial in establishing that many marine reptiles were warm-blooded and in understanding their trophic position in the food web. Biomechanical studies use computer modeling and engineering principles to understand how these animals moved and functioned. By creating digital models of skeletons and muscles, researchers can simulate how the animals swam, how much force their flippers could generate, how deep they could dive, and how fast they could swim. These studies have overturned many long-held assumptions about marine reptile locomotion and behavior. The study of growth patterns in bones, a field called paleohistology, involves cutting thin sections of fossil bone and examining them under a microscope. The growth lines visible in bone cross-sections, similar to tree rings, can tell us how fast an animal grew, how old it was when it died, and even how seasonal variations in food availability affected its growth. This technique has revealed that many marine reptiles grew rapidly when young, reaching sexual maturity quickly, then slowing their growth as adults. Trace fossils, the preserved evidence of ancient behavior, provide another window into marine reptile life. While the tracks made by nothosaurs in ancient seabeds are rare and remarkable finds, other types of trace fossils exist as well. Bite marks on bones show us predator-prey interactions. Coprolites, fossilized feces, can contain bones, scales, and other hard parts of prey animals, providing direct evidence of diet. Stomach stones, or gastroliths, smooth stones found in the body cavity of some marine reptile fossils, might have been used to aid digestion or as ballast for diving. The geographic distribution of marine reptile fossils tells us about ancient ocean currents, migration patterns, and climate zones. Finding the same species in rocks on different continents suggests that marine reptiles could cross ocean basins, following currents or migrating between distant feeding grounds. Finding different species in rocks of the same age from different regions suggests that environmental factors like temperature or food availability created barriers that limited species ranges. Exceptional preservation sites, called Lagerstätten, provide snapshots of entire marine ecosystems. These sites, where rapid burial or unusual chemical conditions preserved not just hard parts, but soft tissues, give us incomparably detailed views of ancient life. Monte San Giorgio in Switzerland and Italy has yielded exquisitely preserved Triassic marine reptiles, including complete skeletons with skin impressions. The Guanling Biota in China shows Middle Triassic marine ecosystems in remarkable detail, with diverse marine reptiles, fish, and invertebrates all preserved together. These exceptional sites also preserve animals that would otherwise be unknown to science. Soft-bodied organisms that leave no fossils under normal conditions can be preserved at Lagerstätten, giving us a more complete picture of marine ecosystems. The interactions between different species can sometimes be captured, as when a predator is preserved with prey still in its stomach, or when two animals are found locked together, perhaps having died while fighting or mating. The fossil record of marine reptiles, while extensive, is far from complete. We have excellent fossils of some groups from some time periods and places, but enormous gaps remain in our knowledge. Many marine reptile species are known from only a handful of specimens, or even just a single fossil. Entire groups might have existed that left no fossils at all, their remains lost to erosion, subduction, or simply the vagaries of preservation. Despite these limitations, the fossil record provides an astonishing amount of information. From scattered bones, we can reconstruct entire animals. From growth lines and isotopic signatures, we can infer their physiology and ecology. From the rocks that contain them, we can deduce the environments they lived in. The science of paleontology is essentially the art of extracting maximum information from minimal evidence, and nowhere is this more apparent than in the study of marine reptiles. New discoveries continue to be made regularly. Amateur fossil hunters still find important specimens. Professional paleontologists discover new sites and new species. Museum collections, some of which have been accumulating for over a century, continue to yield new insights as new techniques allow us to extract information that previous generations of scientists couldn't access. Every year brings new publications describing new species, new anatomical details, new ideas about how these animals lived. The study of marine reptiles also contributes to broader scientific questions. How do organisms adapt to major environmental changes? How do ecosystems recover from mass extinctions? What factors drive evolutionary innovation? Marine reptiles, with their 180 million year history of evolution, diversification, and eventual extinction, provide a natural laboratory for investigating these questions. Understanding Mesozoic marine ecosystems also helps us understand modern ones. The warm climate of the Mesozoic, with its ice-free poles and high sea levels, might be analogous to future climate conditions if global warming continues. Studying how marine life functioned in these warm conditions could help us predict how modern marine ecosystems will respond to climate change. The collapse of marine ecosystems at the end of the Cretaceous shows us how vulnerable even thriving, diverse ecosystems can be to catastrophic change. And so, as you drift toward sleep, comfortable and relaxed, you can carry with you images of these magnificent creatures. The dolphin-like ichthyosaurs with their enormous eyes, hunting through waters that have long since vanished. The long-necked plesiosaurs, impossibly graceful despite their strange proportions, flying through the water on four powerful flippers. The fearsome pliosaurs, apex predators that would have dwarfed any shark alive today. The mosasaurs, gigantic lizards that rose from humble origins to rule the late Cretaceous seas, and all the others, the nothosaurs and placodonts and thalattosaurs of the Triassic, the smaller groups that played supporting roles in this grand drama of evolution and extinction. These animals are gone now, have been gone for 66 million years, but they existed, they thrived, they filled the ancient oceans with life and movement and the eternal struggle to survive. And in remembering them, in learning their stories, we connect ourselves to deep time, to the vast history of life on our planet. We remind ourselves that the world we know is just one frame in an incredibly long film, that the Earth has been home to wonders we are only beginning to understand. Rest now, letting these images and thoughts drift through your mind as you relax completely. The Mesozoic oceans are gone, but their story remains, written in stone, waiting to be read by anyone willing to take the time to learn the language of rocks and fossils. And what a story it is, of ancient seas warmed by a younger sun, of continents moving across the face of the planet, of reptiles that mastered the ocean as thoroughly as dinosaurs mastered the land. It's a story of adaptation and success, of innovation and diversity, and ultimately of extinction and renewal. Sleep well, and may your dreams be filled with warm, clear waters, with sunlight filtering down through tropical seas, with the shadows of great marine reptiles gliding past on their endless patrols. May you swim alongside ichthyosaurs in the open ocean, watch plesiosaurs hunt in the coastal shallows, witness the power of mosasaurs in the late Cretaceous seas, and when you wake, may you carry with you a deeper appreciation for the incredible history of life on Earth, for the countless wonders that have existed in the deep past, and for the fragile, precious nature of the living world that surrounds us today. Before you drift off completely, remember to like this video if you enjoyed this journey through the Mesozoic oceans, and subscribe to Dreamosaurs for more explorations of the ancient world. Share your thoughts in the comments about which of these marine reptiles fascinated you most. Was it the enormous eyes of the ichthyosaurs, the impossible necks of the long-necked plesiosaurs, or the lightning-fast rise of the mosasaurs that captured your imagination? Let us know, and sweet dreams of ancient seas